Last section we explained that sometimes it is mandatory to build a finite element model to extract the fatigue stresses. In this section we are going to explain the different schools in building that model to get the geometrical stresses. We have two main schools, European school and the American school, and we are going to talk about the properties of that model and how you read the geometrical stresses to be able to do fatigue check. Now we will explain the geometrical stresses using finite element modeling. As we explained in the previous section, you have three levels of modeling: global level, macro level, and micro level. And you will have to go through the same three levels to get your geometrical stresses. We will start with the global level. We have a straightforward frame element cantilever truss for our global model, and we are able to plot the combined stresses contour. And from here we locate the location that are mostly stressed from that contour, from this stress contour. That brings us to the next level of modeling, which is macro level. There are two approaches to do the macro leveling. I'll start with approach 2. What you will do, you will go to the most stressed location and start to do a separate submodel that is more detailed and more refined, as we can see here, and give that submodel an appropriate boundary condition to be able to run that model. And then you add a central point at the center of gravity of each element and link that point with the geometry of the element with rigid links. Now you are ready to apply forces important from the global model into that separate submodel at this central point that's rigidly connected to the geometry of elements. You do that yourself. But actually, there are better way to do this using approach 1. In approach 1, you will do exactly the same thing that you have done in approach 2, with a slight difference that will save a lot of time. In approach 2, we still have the same detailed model for the most stressed location, and we still have the central point at the center of gravity of each element that is rigidly connected to the geometry of that element. But instead of applying forces at the central point yourself, what you will do, you will integrate that model into the global model. And how does that look like? It looks like this. So this is the global model. These are the most stressed location where you have your hotspot. You simply integrated the submodel with the global model by rigidly connecting the central point to the rest of the global model. In that case, instead of applying forces yourself at the central point, whatever stresses and forces inside the global model will be automatically transferred to the detailed model at the most stressed location. Once you do that, you are ready to move to the third level, which is the macro modeling. And macro modeling is all about how you are going to model the weld. There are two main schools on this, the European school and the American school. The European school depends on the International Institute of Welding, or the committee that CIDECT, which is committee concerned with the design and construction of tubular structure. So far, they issued 9 design guidelines. It's very useful. Let's start with the European school. In the European school, there are 3 ways to model the weld. First is solid element, and the hot spot will be at the weld toe, as we can see here. The second method is shell element, and the weld itself is modeled as a strip plate shell element, and still the hot spot at the weld toe. The third method is none, and what does not mean? Means that you're not modeling the weld itself, and you believe that rigid connection between the welded plates is enough to represent the weld, and in that case your hot spot is at the intersection of the connected plates. Now let's move to the American school. American school is much more onerous and strict regarding modeling the weld. And it depends if you are modeling the weld for finite life, which is for designing existing construction, or for infinite life, which is used for designing new construction. And you have to do very fine mesh, solid element with a specific dimension and a specific aspect ratio. We will go through this in the slides talking about the American code and how they approach the fatigue design. Now we are ready to read the geometrical stresses. So let's take a closer look near to the weld toes. Early before reaching to the weld toe, stresses are laminar, the stress trajectories are continuous, so stresses here equals to the nominal stresses. Once you get closer to the weld toe, a jump in stresses happen due to the weld geometry. Once you reach to the weld toe itself, right at the weld toe, another big jump happens in the stresses, and that's due to the notch effect created by the weld in the parent metal, and this is called notch stresses. Now you have your finite element stresses. You have this graph where to read the geometrical stresses. We will plot 2 points here, point A and point B, and park them for now until we figure out some concepts. First of all, the Australian code and Euro code follows the European school for modeling the weld. And the European school laid out its method for modeling the weld in two documents: Recommendation for Fatigue Design of Welded Joints and Components, and Design Guideline 8 used for fatigue loading. In these documents, you will find out how we going to model the weld. Okay, and these documents use the theory of critical distance to locate point A and point E, and to use those points for extrapolation to build an extrapolation line. From there, past point A, we can read the geometrical stresses as we can see. So these documents uses the theory of critical distance, which locate point A and point B at certain distance from the weld toe. These points are used to establish an extrapolation line. This extrapolation line past point A enables us to read the geometrical stresses. The location of point A and point E defined by distances LA and LB. And LA and LB depends on the mesh size, whether it's fine or coarse, and it depends what type of stresses you are reading. Are you reading plate surface stresses or plate side stresses, as we can see here in the graph? If you go to those two documents, you will find the whole story about LA and LB and how we get them. Finally, the American school for reading the geometrical stresses. For finite life, when you check an existing structure, American code deals only with point A, and it gives you this formula to locate point A and read the stresses at point A. But if you are designing a new construction, so you have to use the infinite life approach. In that case, you have to read the stresses right at the weld toe, and in that case, you are not reading geometrical stresses. Actually, you are reading notch stresses. As we can see here, LA and LB are located on the different method of modeling for weld, and for when you opt for using this method, so you do not model the weld and you just say there is enough to have these plates rigidly connected, your LA and LB are measured from the point of intersection. And I believe the most convenient method for us for everyday practice should be this method.